The Cafferty Group, technical service advisors with offices located in Nebraska, Iowa, Kansas, and Colorado, presents Gas Combustion Principles. Resources: the Dealer First mobile app. It's quick and easy on-the-go access to warranty express access, matchup and ratings, product and diagnostic information, documents, support, and more. User-friendly interface, available on the Apple App Store or on Google Play. The Partner Link resource for equipment manuals, information, and guides. Go to partnerlinkmarketing.goodmanmanufacturing.com. Log in with credentials. Select option for Communicating Technology or Info Finder Plus. Safety considerations. Recognize these symbols as a safety precaution. As a professional installer or servicer, you have an obligation to know all safety precautions and related items. It is your responsibility to service the product safely. If there is a direct conflict between existing practices and the content of the equipment's installation or service manual, the manual will take precedence. Course content. Module 1, Combustion Theory. Module 2, Components. Module 3, Application. Module 4, Testing. Let's start with Module 1, Combustion Theory, where we will discuss the combustion process. What is combustion? The definition of combustion is the process of burning something. Self-sustaining chemical reaction between fuel and oxygen, resulting in the production of heat and/or light. Thermal energy, heat, is released when chemical bonds are broken and reformed during the combustion reaction. Light is emitted from the flames by small particles glowing incandescently because they are hot, and electrons releasing excess energy in the form of light. Requirements for combustion. 3 items make up the combustion trihedral, and they must be present for combustion to occur: fuel, heat, and oxygen. Each item must have the correct quantity to start and sustain the combustion process. Fuel. Fuels used in the HVAC industry are hydrocarbons. Hydrocarbons are compounds of 2 elements, hydrogen and carbon. Common gas fuels in the HVAC industry are methane, or natural gas. The boiling point of methane at atmospheric pressure is -259 degrees Fahrenheit. And propane, liquid petroleum. Boiling point of propane at atmospheric pressure is -44 degrees Fahrenheit. The natural gas and LP composition: C is a carbon atom, H is a hydrogen atom. Natural gas, methane. Natural gas is a nearly odorless, colorless hydrocarbon blend which is lighter than air. For safety purposes, odorants are added to the natural gas to give it a noticeable odor. Natural gas, primarily composed of methane, may contain ethane, propane, butane, and pentane. BTU content will vary with the mixture. Contact your natural gas supplier for actual BTU content of the fuel. BTU content can vary between 912 to 1,208 BTUs per cubic foot at sea level. National average is 1,025 BTUs per cubic foot at sea level. Heat content of pure methane, 1,011 BTUs per cubic foot at sea level. That's 23,811 BTUs per pound. Liquefied petroleum, or propane. Propane is also a nearly odorless, colorless hydrocarbon blend which is heavier than air. For safety purposes, odorants are also added to propane to give it a noticeable odor. Liquefied petroleum, primarily composed of propane, may contain propane, butane, butene, isobutane, and propene. BTU content will vary with mixture. Contact your LP gas supplier for actual BTU content of the fuel. BTU content can vary from 2,500 to 2,580 BTUs per cubic foot at sea level. Heat content of pure propane, 2,572 BTUs per cubic foot at sea level, or 21,564 BTUs per pound. Stored in tanks as a liquid and vaporized before use. Upper and lower flammability limits. For natural gas, 4% is lean, 10% is about ideal, and 14% is rich. For LP gas, 2% is lean, 4% is ideal, 10% is rich. If the fuel-to-air mixture is on the lean side, there is not enough fuel and too much air. If the fuel-to-air mixture is on the rich side, there is too much fuel and not enough air. Natural gas has a flammability range of 4 to 14%. Propane has a flammability range of 2 to 10%. Heat. Sufficient heat must be present for the combustion process to occur and be self-sustaining. Heat source for ignition must meet or exceed ignition temperatures of the fuel-oxygen mixture. Heat produced by combustion must meet or exceed its fire point to sustain the combustion reaction. Ignition temperature. The temperature at which ignition occurs changes with pressure. It decreases as the pressure is increased, and it increases as the pressure is decreased. It changes with the fuel type and fuel-air ratios. Natural gas at atmospheric pressure has an ignition temperature of 999 to 1,200 degrees Fahrenheit. LP at atmospheric pressure has an ignition temperature of 878 to 1,020 degrees Fahrenheit. Ignition will not occur if the fuel-air ratio is incorrect. Oxygen. Oxygen for combustion is provided by combustion air. Air contains 78.08% nitrogen, 20.95% oxygen, and 0.97% other gases. Combustion air. Fossil fuel burning equipment requires adequate combustion air for safe operation. Quality and quantity of the air must be considered. Contaminated combustion air will result in safety and performance-related problems. For combustion air requirements, refer to the National Fuel Gas Code NFPA 54 ANSI Z223.1 9.3 Air for Combustion and Ventilation. 9.3.2.1 Standard Method. The minimum required volume shall be 50 cubic feet per 1,000 BTUs per hour. In the photograph, notice the high combustion air duct, the low combustion air duct, and the furnace vent pipe. Types of combustion air. There are several different types of air which may be used during the combustion process. Primary air, secondary air, excess air. added to the primary and secondary air, and dilution air. Primary air. Primary air is mixed with the fuel before combustion takes place. It controls the rate of combustion. It controls the amount of fuel that can be burned. Burners are used to prepare the fuel-air mixture. Gas enters the burner through a small orifice. A Venturi effect draws air into the burner and mixes it with the gas. Secondary air. Secondary air is mixed with the fuel after the combustion process has begun. It is air provided to the flames. It helps the fuel burn completely and may be required to complete the combustion process. Secondary air is supplied around the burners at the heat exchanger inlet. Excess air. Air in excess of what is theoretically needed for complete combustion is known as excess air. It's intended to ensure there is enough oxygen for complete combustion. Too much excess air can cause flame impingement, decreases the efficiency of the appliance by lowering the flame temperature, increasing the velocity of the gases in the heat exchanger, absorbing heat from the combustion process and carrying it out of the structure through the venting. Dilution air. Dilution air is added to the fuel gases to assist with venting. It's used only on natural draft equipment. It's provided by a draft hood or a draft control device. It allows air to draft naturally through the furnace and dilutes flue gases, lowering humidity and dew point. Combustion and incomplete combustion. For the fuel and air to properly combust, the mixture must be correct. If not enough oxygen is present or the mixture is incorrect, incomplete combustion will occur. Equipment efficiency will be decreased. Carbon monoxide may be produced. Soot may be produced. Stoichiometric combustion. Stoichiometric, or theoretical combustion, is the ideal combustion process where fuel is burned completely. Stoichiometric ratio is the perfect ideal fuel ratio where the chemical mixing proportion is correct. When burned, all fuel and air is consumed. No leftovers. Understanding the 3 T's. In most fuel-burning appliances, the combustion process is not quite perfect and is affected by the 3 T's. Time. Fuel and air must have time to thoroughly mix. The flame must have time to complete the combustion process. Temperature. Fuel-air mixture must be the correct temperature for proper combustion. And turbulence. Mixing of fuel and air should be complete. Flame and fuel also need to be mixed. The molecular process of natural gas, methane. One methane molecule plus 2 oxygen molecules equal 2 water molecules plus 1 carbon dioxide molecule plus energy is the molecular process of natural gas. Methane contains 1 carbon atom, 4 hydrogen atoms. Oxygen is 2 oxygen atoms. Water, 1 oxygen, 2 hydrogen atoms. Carbon dioxide, 2 oxygen, 1 carbon atom. Carbon monoxide, 1 carbon atom and 1 hydrogen atom. the molecular process of liquefied petroleum, or propane. 2 propane molecules plus 5 oxygen molecules equals 4 water molecules. Add 3 carbon dioxide molecules plus energy makes up the molecular process of LP. Propane, which is C3H8, contains 3 carbon atoms and 8 hydrogen atoms. Oxygen, O2, contains 2 oxygen atoms. Water, H2O, is made up of 1 oxygen and 2 hydrogen atoms. Carbon dioxide, CO2, 2 oxygen atoms, 1 carbon atom. Carbon monoxide, CO, contains 1 carbon atom, 1 hydrogen atom. Byproducts of combustion. Complete combustion results in the following byproducts: heat and light energy, carbon dioxide, CO2, which contributes to global warming, water, H2O, NOx, nitrogen oxides, which contribute to air pollution and global warming. Carbon dioxide. Carbon dioxide is a large contributor to global warming. Natural gas combustion produces about 2.85 pounds of carbon dioxide per 1 pound of methane gas burned, or 120 pounds of carbon dioxide per 1 million BTUs. Propane combustion produces about 3.02 pounds of CO2 per 1 pound of propane, or 139 pounds of CO2 per 1 million BTUs. Water. Every pound of fuel combusted produces water vapor, which is about 12% of the total exhaust by weight. Natural gas combustion produces about 2.25 pounds of water vapor per 1 pound of methane. That's 11.34 gallons of water per 1 million BTUs. Propane combustion produces about 1.6 pounds of water vapor per 1 pound of propane, or 18 gallons per 1 million BTUs. Latent heat. Water vapor in flue gases contain a large volume of latent heat which can be removed from flue gases on condensing furnaces. This occurs by cooling flue gas below water's latent heat of condensation, which is 212 degrees Fahrenheit. Lower dew point equals higher heat recovery. 970 BTUs per pound of water condensed. 1 gallon of water weighs 8.3 pounds. There are 8,051 BTUs recovered per gallon of water condensed. NOx. NOx refers to both nitric oxide, NO, and nitrogen dioxide, NO2. Thermal NOx is formed during the high-temperature combustion process and is determined by the percentage of excess air and combustion temperature. We have oxygen and nitrogen entering the burner as combustion air, and the byproduct of combustion is nitrogen dioxide and nitric oxide. Incomplete combustion of natural gas. 4 methane molecules plus 7 oxygen molecules equals 8 water molecules. Add 2 carbon dioxide molecules and 2 carbon monoxide molecules, plus energy. So the molecule types: methane, CH4, 1 carbon atom, 4 hydrogen atoms. Oxygen, O2, 2 oxygen atoms. Water, H2O, 1 oxygen atom, 2 hydrogen atoms. Carbon dioxide, CO2, 2 oxygen atoms, 1 carbon atom. Carbon monoxide, CO, 1 carbon atom, 1 hydrogen atom. Incomplete combustion of LP, propane. 2 propane molecules plus 9 oxygen molecules equals 8 water molecules. Add 4 carbon dioxide molecules, 2 carbon monoxide molecules, and energy. Molecule type breakdown is still the same. Byproducts of incomplete combustion. Incomplete combustion is unsafe, unpredictable, and results in unknown quantities of byproducts: heat and light energy, water, carbon dioxide, which contributes to global warming, carbon monoxide, poisonous, colorless, odorless gas. Carbon may appear in the form of soot. NOx refers to both nitric oxide, NO, and nitrogen dioxide, NO2. Carbon monoxide, CO. Carbon monoxide is a poisonous, odorless gas that can cause illness, sickness, and death. Levels as low as 3 parts per million can cause health issues. The effects of carbon monoxide poisoning will vary with a person's length of exposure, health, age, and physical size. From 0 to 4 parts per million over a duration of 8 hours is considered good air quality, according to the EPA. 35 parts per million for a duration of 8 hours is a recommended 8-hour maximum workplace exposure, according to the National Institute of Occupational Safety and Health. 50 parts per million for a duration of 8 hours is the recommended 8-hour maximum workplace exposure, according to the Occupational Safety and Health Administration, OSHA, permissible exposure limit. 400 parts per million for a duration of 1 to 3 hours. Healthy adults will suffer headaches, dizziness, and nausea in 1 to 2 hours. Life-threatening after 3 hours, according to the CDC and NIOSH. 800 parts per million for less than 2 hours. Healthy adults will suffer headaches, dizziness, and nausea in 45 minutes, unconsciousness or death in less than 2 hours, according to the CDC and NIOSH. 3,000 parts per million, less than 30 minutes exposure, can cause death in less than 30 minutes, according to the CDC and NIOSH. Causes of carbon monoxide. Carbon monoxide, CO, will usually be present in flue gases. The combustion process is not 100% perfect. The worse the process is, the greater the concentration of CO in the flue gases. Gas furnaces may produce carbon monoxide if you have insufficient oxygen for the amount of fuel that's present, the fuel and air are not properly mixed, you have insufficient combustion air, the burner flame is impinging on a surface, it's not vented properly, or there's a crack in the heat exchanger that prevents complete combustion. Soot. Soot is a black, powdery, or flaky substance consisting mostly of carbon that can be produced by incomplete combustion. It indicates the furnace is not functioning properly. Carbon monoxide levels will likely be higher. It reduces heat transfer by acting as an insulator and lowers efficiency. It can block flue passages and the heat exchanger. Its makeup is 4 molecules of CH4 plus 7 molecules of O2 equals 8 molecules of water plus 2 molecules of carbon dioxide and 2 molecules of carbon plus energy. Module 2. Components. Forced air furnace. Forced air furnaces use a motor and blower wheel to move air across the furnace heat exchanger. When air passes across the heat exchanger's hot surface, the air temperature rises. Forced air furnaces move air throughout a home faster and more efficiently than natural convection or gravity flow equipment. It utilizes smaller heat exchangers and ductwork than convection equipment. Integrated furnace control. Induced draft and condensing furnaces use an integrated furnace control to ensure safe operation. It monitors furnace safeties. It controls operation of the furnace components, such as the draft inducer, the igniter, the gas valve, and the indoor blower operation. It determines if flame is present, and if it detects something wrong, it shuts off the burner. Blower motor. The blower is used to generate airflow into a home by means of supply and return air ductwork. The blower circulates air throughout a home by pulling in cool air through the return ductwork and air filter, pushing that air through the heat exchanger, and supplying warm air to the home by means of the supply ductwork. Furnace heat exchanger. When gas burns, poisonous gas, including carbon monoxide, are emitted. To keep the poisonous gases separate from the air, a heat exchanger is used. Most heat exchangers are simply S-shaped metal tubes. Gas flames burn inside the tubes. Poisonous gases are vented out through the flue pipe, and the blower moves air around the outside of the tubes. Here's an example of an 80% induced draft furnace and a 90% condensing furnace. The blower pulls cool air or return air into the furnace. It blows that air across the heat exchanger, absorbs heat from the heat exchanger, and distributes it into the supply air ductwork to heat the home. Draft inducer. Induced draft and condensing gas furnaces use a draft inducer to vent the byproducts of combustion out of the home through a venting system. The draft inducer operates before combustion begins, a pre-purge period, brings fresh air into the heat exchanger. During combustion, the run cycle, it pulls burner flames and secondary air into the heat exchanger, pushes the flue gases into the vent. After combustion, the post-purge period, it removes any leftover combustion byproducts. Gas valve. A residential furnace gas valve serves two purposes. It starts and stops the flow of fuel, and it regulates the amount of fuel pressure going to the burner orifices. It must be set per manufacturer's recommendations. Most residential furnaces operate with a manifold pressure of 3.5 inches of water column for natural gas, 10 inches of water column for propane. Manifold pressures for natural gas, on low stage, the range is 1.6 to 2.2 inches of water column. Nominal is 1.9 inches of water column. High stage, 3.2 to 3.8 inches of water column. Nominal, 3.5 inches water column. For propane or LP, low stage, 5.7 to 6.3 inches water column. Nominal, 6.0 inches water column. High stage, 9.7 to 10.3 inches of water column. Nominal is 10 inches of water column. Limit switch. If a furnace becomes too hot, a limit switch is used as a safety to stop the flow of gas to the burners. For example, if a blower motor stops working and no air is being circulated, temperatures will rise inside the furnace. If this happens, the limit switch will shut off the power to the gas valve until the problem is fixed. There are various limits that will be used in furnaces. Some examples are below, such as a primary limit, rollout or burner limit, and an auxiliary limit. Igniter. Residential gas furnaces will use one of several different methods to ignite the fuel-air mixture. Natural draft equipment commonly uses a standing pilot. Older induced draft equipment may use an intermittent spark ignition. Newer induced draft equipment and condensing furnaces use hot surface or direct spark ignition. Ignition source must meet or exceed ignition temperature of the fuel-oxygen mixture. Flame sensor. A flame sensor is a device that is used in conjunction with the ignition control module to improve combustion. If proof of flame is not present, the control will de-energize the gas valve and retry for ignition or lockout. Current flows from the sensor through the flame to the burner head, then to ground. Current flowing through the flame is rectified, resulting in a pulsating DC current. DC current pulsating to the board confirms ignition. The current is measured in microamps. Burners. There are several different types of burners used in residential gas furnaces. The in-shot burner is used on newer equipment and uses primary and secondary air. The premix type burner, commonly used on ultra-low NOx equipment, uses primary air and controls excess air. The ribbon burner is used on older equipment and uses primary and secondary air. Some burners may have built-in primary air adjustment. The burner's job is to thoroughly mix the fuel and primary air, direct the flame into the heat exchanger, retain the flame and prevent it from blowing off the burner, called blow-off. Arrest or contain the burner flame to prevent it from going inside of the burner, called flashback. and allow the flame to cross over to additional burners. Here's a diagram showing the gas orifice, the venturi, and the crossover, and a magnified view of the crossover. Ultra-low NOx burners. Ultra-low NOx burners pre-mix fuel and air to reduce NOx emissions by reducing flame temperatures, because the burner creates larger, more spread out flames which have a lower peak temperature. And the heat exchanger may have flame impingement inserts to reduce the flame temperature. It also limits excess air because lower excess air levels starve the reaction for oxygen. Burner orifices. Furnace burner manifolds have gas orifices which regulate the flow of gas to each burner. Orifices must be sized per manufacturer's recommendations. The size is usually stamped on the orifice. Natural gas orifices are generally larger than propane orifices due to lower burner manifold pressures. Check the orifices for dirt, distortion, and burrs. It should be removed and installed with a box end or socket wrench to prevent distortion. Let's review what we've covered in this section. Which furnace component separates the combustion products from the air? The heat exchanger. What two functions does the gas valve perform? It starts and stops the flow of gas, and it regulates the amount of fuel pressure going to the burner orifices. How does a flame sensor circuit prove that the flame has been established? It allows a small amount of DC current to pass through the flame, measured in microamps. Ultra-low NOx burners reduce nitrogen oxide emissions by reducing flame temperature and limiting excess air. Module 3, Application. Learning objective. We will discuss burner flame and learn the types of draft. First, let's take a look at standing pilot ignition. The standing pilot general sequence of operation. The pilot is lit manually. The thermocouple powers the pilot gas valve. If the pilot goes out, the valve will close. If any safety circuits are open, voltage to the gas valve will be interrupted. Safety circuits would be high limit, auxiliary limit, flame rollout, or a spill switch. Sequence of operation starts on a call for heat. Is the pilot lit? If yes, it verifies that the safety circuit is closed. If the pilot light is not lit, or the safety circuit is not closed, the furnace will not operate. If the pilot is lit and the safeties are all closed, the gas valve is energized. The blower energizes after the heat exchanger warms up. Then when the call for heat ends, the main gas valve closes and extinguishes the flame. The blower motor turns off after the heat exchanger has cooled down. Intermittent pilot ignition. Intermittent pilot general sequence of operation. The spark igniter lights the pilot, which then lights the burners. The pilot stays lit after the burner ignition. The ignition control continually monitors internal self-diagnostics and furnace safety circuits. That means it will shut down the burners if any fault or open safety circuits are detected, such as high limit, auxiliary limit, loss of flame, loss of draft, or flame rollout. Since this system contains an integrated control module, the full sequence of operation is as follows. The sequence starts with a call for heat. It goes into a self-diagnostic state. If the self-diagnostics fail, then a fault code is produced and the furnace is locked out. If the self-diagnostics passes, the inducer motor will start. Once the inducer motor starts, the draft pressure switch will close. If it does not close, it sets a fault code and will retry and starts the sequence over again. If the pressure switch still doesn't close after trying a pre-programmed number of times, the furnace locks out. If the draft pressure switch closes, indicating that the exhaust is flowing freely, then the pre-purge period begins. After the pre-purge has expired, then the spark igniter and the gas pilot are energized. It checks for flame. If it does not detect flame, then a fault code is produced and the sequence starts over again. If flame is not detected after retrying a pre-programmed number of times, the furnace is locked out. If the flame is detected, the gas valve opens and lights the burners. The igniter is then de-energized and the blower-on delay begins. When the blower-on delay time is reached, the blower turns on and runs until the call for heat ends. The main and the pilot gas valve close, the flame is extinguished, and post-purge period and blower-off delay begin. After the post-purge period expires, the inducer draft motor shuts down and the blower-off delay begins. And then the blower turns off after the blower-off delay expires. Interrupted pilot ignition. Interrupted pilot general sequence of operation. The spark ignites the pilot, which then lights the burners. The pilot goes out after burner ignition. Ignition control continually monitors the internal self-diagnostics and furnace safety circuits. This will shut down the burner if any fault or open safety circuits are detected, such as high limit, auxiliary limit, loss of flame, loss of draft, flame rollout. The main sequence of operation on a call for heat is the same as the intermittent pilot ignition sequence, with the exception of, after the gas valve opens and the burners light, the ignition and the pilot gas are de-energized. Direct hot surface ignition, or HSI. HSI, general sequence of operation. The hot surface igniter directly ignites the burners. Ignition control continuously monitors the internal self-diagnostics and furnace safety circuits. The system will shut down if any fault or open safety circuits are detected, such as high limit, auxiliary limit, loss of flame, loss of draft, flame rollout. The detailed sequence of operation is the same as the interrupted pilot ignition, except there is no pilot gas. Direct spark ignition, DSI. DSI, general sequence of operation. The spark igniter directly ignites the burners. The ignition control continually monitors the internal self-diagnostics and the furnace's safety circuits. This will shut down the burners if any faults or open safety circuits are detected, such as high limit, auxiliary limit, loss of flame, loss of draft, flame rollout. The detailed sequence of operation since it uses an integrated control module, are the same as the HSI ignition system. Parts of the flame. There is a clear, unburned fuel-air mixture. There is a bright blue inner cone, and a dark blue outer cone, and the outer mantle. Flame color. The color of a flame depends on a variety of conditions, such as temperature, chemical composition, and the amount of oxygen present. Natural gas and propane burner flames should be stable, soft, and blue, and not curling, floating, or lifting off the burner. Orange and yellow flames. Flame color can help identify issues. A yellow or orange flame may indicate there's not enough oxygen present to complete combustion. There may be contaminants present in the fuel. The flame is impinging on something, and dust may cause orange streaks which randomly appear and disappear. Flame condition. Dangerous flame conditions. Flame rollout occurs when the fuel-air mixture is not drawn into the heat exchanger properly. A lazy flame can occur when flames are not drawn into the heat exchanger properly, the fuel-air mixture is incorrect, or the velocity of the fuel-air mixture is too low. Flames may be yellow or blue, depending on the amount of oxygen present. Flame blow-off and flashback. Velocity of the fuel-air mixture must be correct, or flame blow-off or flame flashback could occur. Fuel-air velocity that exceeds the flame's propagation rate will cause the flame to blow off the face of the burner. Flame propagation rate is the speed at which the flame progresses through the fuel-air mixture. Fuel-air velocity that goes below the burner's ability to arrest the flame may flash back onto the burner. This can also occur when the flame is extinguished, possibly resulting in extinction pop. Stack draft. Stack draft is required on all induced draft and natural draft equipment. It's created by warm air rising through the vent piping. It must produce a slight negative pressure at the vent inlet. It's used to carry flue gases out of the structure. If the stack draft is too high, it can affect excess air on your burners. If it's too low, the appliance may not vent properly. It is not required for condensing gas furnaces. Overfire draft. Natural draft furnaces and water heaters have overfire draft. It's created by warm air rising through the heat exchanger. Overfire draft creates a slight negative pressure at the heat exchanger inlet. It controls the speed of the flue gases in the heat exchanger. High overfire draft decreases efficiency by allowing high volumes of excess air to be heated and reducing flue gas contact time with the heat exchanger. Review. Natural gas and propane burner flames should be stable, soft, and blue. Orange and yellow flames may indicate Not enough oxygen is present to complete combustion. Contaminants are present in a fuel, or flame is impinging on something. When does flame rollout occur? When flames are not drawn into the heat exchanger properly. Stack draft is required on which type of equipment? All natural and induced draft equipment. Module 4. Testing. Learning objective. We will discuss testing methods and learn how to determine correct readings. Combustion analyzer. The best way to check combustion is to use a quality combustion analyzer which can test for percentage of carbon dioxide, parts per million of carbon monoxide, percentage of combustion efficiency, percentage of excess air, flue temperature, NOx parts per million, and a percentage of oxygen. Natural draft furnace and water heater test locations. Flue gases on natural draft equipment must be tested before dilution air is added. If dilution air is added, readings will be incorrect. This may require reading to be taken at the heat exchanger outlet. Adjusting each individual burner or burners for fuel-air ratio may require testing of individual heat exchanger sections. Induced draft and condensing furnace test locations. Flue gases must be tested as close to the furnace outlet as is practical. It should be in the vent line close to the furnace connection. Insert the sampling probe halfway into the vent pipe at a 90-degree angle. The opening in the vent pipe must be sealed after use. Test procedure. Follow the instructions for the model of analyzer you are using to ensure your readings are accurate. Start the equipment and let it reach a steady state condition. Test all stages. Modulating equipment should be tested in low, mid, and high stage. Take multiple samples from outdoor, indoor, and flue. Record your readings. Compare them to the equipment manufacturer's recommendations. Carbon dioxide. The amount of carbon dioxide contained in flue gases is dependent on the carbon content of the fuel. Carbon dioxide is measured in percentages. Natural gas maximum CO2% is 11.8. although the maximum theoretical level is never reached in practice. Optimum is 10%. Typical is 6.5 to 8%. Propane maximum CO2% is 13.7, although the maximum theoretical level is never reached in practice. LP is slightly higher than methane due to propane's higher carbon content. Optimum is 12%. Typical is 8 to 10%. Correlation of the percent of CO2, O2, and excess air. These are approximated values for CO2 and O2 in the flue gas as a result of excess air. When a change is implemented that affects either CO2, O2, or excess air, that change affects the other two as well. You can see by the chart below As the percentage of excess air increases, the percentage of CO2 in the flue gas decreases, and the percentage of oxygen in the flue gas increases. Carbon dioxide calculator. The maximum possible CO2 exhaust concentration depends ultimately on the carbon content of the fuel being burned. For example, for natural gas, the maximum CO2 is 11.8%. The measured O2 is 7%. The percentage of CO2 by volume is 7.78. So let's do a calculation. The percentage of CO2 by volume equals the CO2 maximum times 20.9 minus the measured O2 percentage over 20.9. That would be 20.9 minus the measured O2, which is 7, over 20.9. That would be 13.9 divided by 20.9. So the CO2 by volume is the CO2 maximum times 0.66. The maximum CO2 is 11.8. So we would take 11.8 times 0.66, which would give us 7.78% CO2 by volume. Carbon monoxide. Ideally, carbon monoxide in flue gas should be as low as possible, but must meet minimum standards. It is measured in parts per million. Measurements taken from flue gases are before dilution air is added. 100 parts per million is the maximum National Comfort Institute CO level during a run cycle in all vented appliances operating in a stable condition. ANSI Z21 maximum CO level is 400 parts per million, air-free for vented heating equipment. For leakage from appliances, 9 parts per million is ASHRAE's standard for allowable spillage from vented appliances indoors for an 8-hour period of exposure daily. Air-free carbon monoxide measurement. ANSI, the American National Standard Institute, Z21 air-free, is used to determine the concentration of carbon monoxide in flue gas if all excess air was theoretically removed. Readings are taken from undiluted flue gas, and they use a mathematical correction to provide an air-free CO measurement. In this example, the oxygen in the air is 20.95%. Measured CO by use of a combustion analyzer is 50 parts per million. Measured O2 by use of a combustion analyzer is 6%. Air-free CO is 70 parts per million. Let's look at how we arrived at that number. So the air-free carbon monoxide is the measured carbon monoxide in parts per million times 20.95, which is the oxygen in the air, divided by 20.95 minus the O2 level in the flue gas. That would be 20.95 divided by 20.95 minus 6% measured oxygen in the flue gas. That would give us 20.95 divided by 14.95. So the air-free CO is 50 parts per million times 1.4, which is 70 parts per million. Carbon monoxide during ignition and shutdown. When a burner ignites, a large amount of carbon monoxide may be produced which can cause a surge in the flue gas CO readings for the first 60 seconds. This should not exceed 400 parts per million for natural draft furnaces, or 1,000 parts per million for induced draft and condensing furnaces. After 5 minutes, the CO levels should be below 100 parts per million and stable. When the furnace shuts down, the CO levels should fall. If the CO level rises, the burners may not have shut down properly. Air-free CO levels may rise if the combustion analyzer O2 sensor reacts more quickly than the CO sensor. Rising carbon monoxide. Anytime CO is rising and unstable at any level from 1 part per million to 400 parts per million during the combustion process, the burner should be shut down and/or immediately tested and repaired. A burner with rising CO is far more dangerous than a stable reading because the CO could continue to rise above dangerous levels. Stack draft test. To verify that flue gases are being properly removed through the vent system, a draft test should be performed. Natural draft equipment should be tested in the vent line after the dilution air is added. Induced draft furnaces should be tested in the vent piping close to the furnace connection. Condensing gas furnaces do not require a draft test. Stack draft readings. Use a draft gauge to measure the draft of the equipment's vent. During all testing, the draft should be between 0.01 inches water column and 0.02 inches of water column, according to the National Comfort Institute. Typical is between 0.02 and 0.04 inches of water column. Draft interference can be caused by fan interference, building pressure, wind effect, improper combustion air, flue design, flue gas temperature, and stack effect, which is pressure difference created by thermal difference. Draft verification. During steady-state operating conditions, the draft should be stable. Draft will increase with temperature. Once the maximum temperature is reached, the draft should stabilize. Natural draft equipment may take several minutes for the draft to be established. Under ANSI, the American National Standards Institute, standards, an appliance has 5 minutes to prove draft. If draft-induced and atmospheric appliances are common vented, verify that the flue gases are not spilling out of the draft hood on the natural draft furnace when the draft-induced furnace is operating. Verify that the natural draft furnace is not spilling flue gas when both furnaces are running. Excess air. The combustion efficiency increases with increased excess air until the heat loss in the excess air is greater than the heat provided by more efficient combustion. Natural gas requires 15 cubic feet of air per cubic foot of fuel, 10 cubic feet for combustion, and an additional 5 cubic feet to ensure complete combustion. Propane requires 37.5 cubic feet of air per cubic foot of fuel, 25 cubic feet for combustion, and an additional 12.5 cubic feet of air to ensure complete combustion. Typical excess air to achieve the highest possible combustion efficiency is 10 to 20% optimum. that range from 40 to 75%. The typical furnace is 40 to 50%. Excess air oxygen versus flame temperature. As you can see by this chart, the flame temperature decreases as the percentage of oxygen in the excess air increases. Excess air calculator. Let's look at how to calculate excess air using the oxygen percentage. In this example, the measured oxygen level in the flue gas, determined by use of a combustion analyzer, is 6%. The amount of excess air is 40.3%. So the formula is the percentage of excess air is the percentage of O2 measured using a combustion analyzer divided by 20.9, which is the percent of oxygen in the air, minus the percent of O2 that was measured, times 100. So the measured O2 was 6%. So we take 6% divided by 20.9 minus 6% times 100 is 6% divided by 14.9 times 100. So the excess air is 0.403 times 100, or 40.3%. NOx. Combustion NO is generated as a function of air-to-fuel ratio and is pronounced when the mixture is on the fuel lean side of the stoichiometric ratio. It is measured in parts per million. Residential furnaces have no provision for NOx adjustment. California's South Coast Air Quality Management District, Rule 1111, and San Joaquin Valley Air Pollution Control District, Rule number 4905, require NOx emissions of less than 20 parts per million. Other parts of California require less than 55 parts per million. Oxygen. Oxygen levels should be set correctly to minimize wasted heat from excess air and reduce NOx emissions. The National Comfort Institute recommended oxygen readings for natural draft and induced draft furnaces should be between 6 and 9% and remain stable. Oxygen readings below 6% are acceptable if carbon monoxide levels are below 100 parts per million and stable. Flue temperature. Heat leaving the exhaust flue with hot gases is not transferred to do any useful work. Fuel efficiency drops as the flue temperature increases. On non-condensing furnaces, the temperature in the flue needs to remain high enough to avoid condensation inside the vent. The National Comfort Institute recommended flue gas temperatures are 415 to 525 degrees Fahrenheit for natural draft furnaces, 302 to 402 degrees Fahrenheit for induced draft furnaces, 100 to 140 degrees Fahrenheit for condensing gas furnaces. Combustion diagnostics table. We're going to look at the NCI, carbon monoxide and combustions diagnostic table. This can be used to help diagnose specific problems using carbon monoxide, oxygen, draft, and flue temperatures when applicable. The NCI carbon monoxide and combustion diagnostics table takes into account the condition, and depending on the condition, you can diagnose problems by getting readings for carbon monoxide parts per million, carbon monoxide action, oxygen action, flue temperature change, flue draft, which burners are affected, and the final assessment method. So if your condition was overfired, your CO would be over 100 parts per million. CO action could be stable. However, if you have an induced draft system, the CO action will normally rise in an overfired condition. Oxygen would be low. Flue temperature change would be high. The burners affected would be selective. And the final assessment method would be measurements with a combustion analyzer. On an underfired system, the oxygen action would be high, the flue temp change would be low, the burners affected would be selective, and final assessment would require measurements. Venting problems. The carbon monoxide parts per million would be rising. The carbon monoxide action would be rising. Oxygen action would be falling. Flue draft would be high. The burners affected would be selective, and final assessment would require measurement. Combustion air condition. Carbon monoxide parts per million would be rising. Carbon monoxide action rising. Oxygen action falling. Flue draft low. The burners affected would be all, and would require measurement for final assessment. Dirt or rust. The carbon monoxide level would be over 100 parts per million. Carbon monoxide action would be stable. Oxygen action normal. Burners affected would be selective. The final assessment method would be visual. Alignment. CO would be over 100 parts per million. CO action stable. Oxygen action normal. Selective burners. And final assessment would be visual. If it was a mechanical problem, CO would be over 100 parts per million. CO action stable. Oxygen action normal. Burners affected would be selective. The final assessment method would be visual. Heat transfer. The flue temp change would be high. All of the burners would be affected, and it would take a measurement for the final assessment. 80% induced draft furnace example. Induced draft gas-fired burners in the 80% AFUE category. Efficiency 80 to 82%. Oxygen 7 to 9%. Carbon dioxide 6.5 to 8%. Stack temperature 325 to 400 degrees Fahrenheit, or 170 to 270 degrees above supply air temperature. Draft 0.02 to 0.004 inches of water column. Carbon monoxide below 100 parts per million undiluted, maximum 400 parts per million air-free. 90% condensing furnace example. Draft sealed combustion induced gas-fired burners. 90 plus AFUE. Efficiency 88 to 92%. Oxygen 5 to 7%. Carbon dioxide 7 to 8.5%. Stack temperature less than 130 degrees Fahrenheit. Draft 0.02 to 0.08 inches of water column. Carbon monoxide less than 100 parts per million undiluted, maximum of 400 parts per million air-free. Review. Which tool is required to test combustion on a natural gas or propane furnace? Combustion analyzer. Combustion readings must be taken before dilution air is added. True or false? True. Oxygen levels below 6% are acceptable if the carbon monoxide levels are below 100 parts per million and stable. Flue gas temperature of a condensing gas furnace should be between 100 degrees Fahrenheit and 140 degrees Fahrenheit. Thank you for joining us for Gas Combustion Principles. If you have any questions or need more information, please contact your local Cafferty Group Technical Service Advisors at one of these 12 locations.